Question number 3. How many isomers are represented by C5H12? So there could be 5 in a line, which is pentane. There could be 4 in a line with a methyl group at number 2, 2-methylbutane. 2-methylbutane and 3-methylbutane are the same thing. It just depends which end you start labeling from. Methylbutane or 2-methylbutane, same thing. Or I could have 3 in a line propane with 2 methyl groups on number 2. So I could have dimethylpropane. So there are 3 different isomers. Name the type of structural isomerism shown by C5H12. So structural isomerism, remember, is the same molecular formula but just a different structural formula, so it's drawn in a different way, in a different structure. And there are 3 types: chain isomerism, where the length of the chain changes; position, where the position of a functional group changes, maybe a double bond changes its position, or an OH changes its position on the chain; and a functional group, where the actual functional group changes, so maybe it changes from a double bond to a cyclic set of single bonds, something like that. In this case, pentane has shortened its chain to methylbutane, shortened its chain again to dimethylpropane. It's chain isomerism. So the next one, 2-hydroxypropane nitrile, displays optical isomerism. So I've drawn you 2-hydroxypropane nitrile here. Let's just have a look at it. Prop, 3 in a line. 2-hydroxy, so an OH is either an ol or an hydroxy. Propane, 3 in a line. Nitrile is a CN, and the C, one of the C's counts as part of the chain. So I've got 3 carbons in the chain. This is a nitrile, and since this ends in the word nitrile, and by the way, that C is always number 1 there, the C of the CN is always at number 1 because this group is always at the end of a chain. This makes this number 2. And since I've used the ending nitrile, I need to name this as a group, a hydroxy group. Now it says draw two three-dimensional representations of the 2 enantiomers. So this enantiomer, because the carbon in the middle is a chiral carbon or an asymmetric carbon, it's got 4 different groups attached to it, so it's going to have mirror images enantiomers that will rotate plane polarized light in different directions. So let's have a look at this. So I've got to draw the 3-dimensional representations of this. Normally you can get away with just drawing a 2-dimensional representation, drawing a cross shape and then drawing again with the CN on this side and the CH3 on the right hand side, the OH up and the H down. But it wants you to do a 3-dimensional representation. So what you need to do is you need to draw the OH and the H, or any of these groups really, let's say the OH and the H, and then one coming forward, let's say the CN, and the CH3 going backwards with a hash line. But these can be in any position you want really. I've just got a drawing of it like this. But then you do the mirror image with the CH3 reversed, the C here, the OH there, like that. I suppose the O and the H should really be on the left, I suppose, but you get the marks for that anyway. An H on the right hand side and a CN here. So it's a direct mirror image, and you have to draw the 3-dimensional representation because it asks for a 3-dimensional representation. As I say, normally you can get away with a 2-dimensional representation. Describe how these separate samples of each of the enantiomers could be distinguished. They rotate plane polarized light in different directions, so in opposite directions or in different directions. You've got to have the word rotate, you've got to have the word plane, and you've got to have the word polarized light in different or opposite directions.